There's a tape in there too, Rich? In the camera? Okay. All right. Hope everybody had a good weekend. One of the things that I want to constantly emphasize, through the whole presentation of this class is taking things that are or can be complex and simplifying them. Okay? If we're not doing that, meaning me as the instructor, if I'm not doing that, okay, then you as the student, need to let me know. Raise your hand, ask me if I can explain it in a different way, or there's another way to look at it, or there's another formula that could be used, or whatever. Sometimes it's just a matter of it being new and just practicing with it. It's just like, riding a motorcycle. Teaching somebody young to ride a motorcycle. You put them on it, they've ridden a bike, so they got the basic idea of, balance and center of gravity, but, they don't have the clutch quite down, they don't have the shifting the gears down, they don't have the throttle synchronization down, so it just takes a little while. And then after a little while, there's some muscle memory that builds in, and it becomes as automatic as riding a bike. The analogy is just as valid here. I may show you something, and the first time you see it, even though when I explain it, it seems like it's pretty straightforward, but then you go and try to do it the first time, you may have a little trouble. Don't get frustrated at that. As a matter of fact, one of the things that got me through school was a hint that a professor gave me one time, and that was to expect it. He said, whenever something comes along that you're trying to learn and you're having trouble with it and you really just can't digest it, like to the point where you can explain it, you're not there. You've only heard it explained once, you're trying to do it for the first or the second time, and you're just not getting it, okay? Then say to yourself, okay, I'm right where I'm supposed to be. I'm right where I'm supposed to be. Because if you could get it the very first time, every time, then, you'd probably be, number one at Harvard or something, right? I mean, if you had an IQ of, 190, you'd be one in, a billion people, right? So for the rest of us mere mortals, right, we have to use a little bit of muscle memory. And so what I find is that with the stuff that we're doing with AC, if you just are patient and pay attention to working on your crib sheet, working on your summary sheets, and refining them so that you get more and less space, and you get to where you can explain what you've written down on the paper. Okay, then it just starts getting easier and easier and easier. Just like the first time you tried to ride a motorcycle, and then now it's your second week of trying to ride the motorcycle. You're going to be a lot better at it. Okay, so what we're going to do today is we are going to revisit something that last week, but we're going to revisit it a little bit different. Okay, in this schematic diagram, we have an AC source of some kind, which could be anything from a Honda generator to Diablo Canyon nuclear power plant. We don't know what it is. It's just supplying enough voltage and enough current to drive our load. Okay, that's our assumption. We also have an inductor, which is simply a coil of wire that's wrapped around what? Ferrous metal, ferromagnetic core. So there's a ferromagnetic core that's wrapped around it, and then we have a resistor. So there's an L which is rated in henries. And there's an R, which is the magnitude of opposition to current flow with dissipation of heat. Remember, the main difference between these two in terms of heat is that this guy dissipates heat, this guy doesn't. Okay? Now, if you say to me, well, wait a second, I've worked with inductors before, and if you tell me they don't get warm, I don't know, because the ones I've dealt with have gotten warm. Yes, they do get warm, but it's not because of the pure inductance that they get warm. It's because of the resistance in the winding. In other words, you can't make a winding without using wire, right? And the wire has resistance in it. So because of that, you're going to have some dissipation of heat in the inductor, okay? But the true pure inductance offers opposition to current flow, just like walking through the pool, just like the example we used way back, right? It offers opposition to AC current flow, okay, but it dissipates no heat. So if there were a pure inductor in the circuit and no resistance, which is theoretically impossible, because you can't make an inductor without resistance, okay? But if you could do that, like let's say with a superinductor or something, okay, you would dissipate no heat. In other words, the inductor would absorb some energy, right, because it's an energy storage device. So it would absorb some energy, and then on the next half cycle, it would deliver the energy back to the source. So it would be like a teeter-totter, right? Like part of the time you're having to put energy into getting the thing to go up, and then you go up, and then you can just hang there, and then you just fall down due to the force of gravity and the other person pushing off the other end. And then when you hit the ground, you got to go up, and then the other person hits the ground, and then they go up, right? So it's an exchange. You're putting energy in, and then putting energy back, then putting energy in, and then getting energy back. Okay. Now, as far as what it's good for, we've talked about the use of filters, and that's a big part of this course. And we're just not there yet because we just haven't worked enough of these problems yet to design filters. Okay, but when we get there, then the analysis part of this will hopefully be like, I don't know, the 6th week of riding your motorcycle, right? And you're going to be fairly comfortable with the clutch and the throttle and synchronizing everything, right? And you're going to be able to start negotiating a little hill, right? And that's going to be our filter, okay? All right, so let's just say that in this problem right here, that the source voltage is something that we don't know. Okay, that's an unknown in the problem. Let's say that the frequency is equal to 1 kilohertz, which is the same thing as 1,000 hertz, right? Because 1 kilohertz is 1,000. The formula for inductive reactance is X of L is equal to 2 pi frequency times inductance. Okay? But what we're going to do is we're going to give this inductor an inductive reactance that's equal to 420 ohms. Okay? So basically, this formula allows us to go from the unit of henries to the unit of ohms. And all we're doing is we're just saying we've already done that calculation and we found out that this is 420 ohms. Okay? And then the resistor has a value of 273 ohms. Now, what we want to do is start to get comfortable with what's going on in the circuit. Okay? One of the things that we can look at and by inspection tell right away is that all of the components are connected in what configuration? Series. Right. So this is a series circuit. It's a series circuit because the current through every component has to be the same. In other words, there's no way for it to branch off. Okay? We know it's a series circuit. We also know that the current that's flowing from the source will be related to, in what way, the current flowing through the resistor. What can you say about their relationship? They're the same. They're equal. So the current from the source is equal to the current in the resistor, which is equal to the current in the inductive reactance. Okay? So just by looking at that circuit, you should start to be comfortable with those principles. We got a series circuit, we got an inductor, we got a resistor. Okay? This time what we're going to do is we're first going to figure out what the voltage of this circuit is. Okay? Because we don't know what the voltage is. Okay? And then we're going to focus on how the power distributes through the circuit. That's going to be really the main focus of this session. Okay, the power triangle. We have three different types of power. We've talked about them before. Does anybody remember what they are? We got the power that's dissipated by a resistor. What kind of power? What's the unit on that? Watts. Watts. So the power that's dissipated by a resistor is watts. The power that's dissipated by a reactive component, like a capacitor or an inductor, is what? Begins with a V. VARs. And that stands for volt amperes reactive. And then the power that the source dissipates is what? Volt amperes. VA. Because remember, power equals volts times current. VA. Okay? So, well, let's do this. Since we did that last time, let's go ahead and give this a voltage. Somebody just pick a voltage. 50 volts. Okay? And then what we're going to do is move to the right a little bit here, and we are going to discuss the power triangle. Okay? Now, in the very beginning of the course, when we were dealing with just straight Ohm's law, okay, we had three formulas for power, if you remember, in the Ohm's law wheel. One of them was power equals voltage times current. One of them was power equals current squared times resistance. One of them was power equals voltage squared over resistance. And from each one of those formulas, we got watts, because we were dealing with DC circuits. We were dealing with purely resistive circuits. And purely resistive circuits dissipate heat in the form of watts. Okay? A power triangle still shows the watts that are dissipated in the circuit. But what it does is it shows the whole picture. You know, it's like going from black and white TV to going to color TV. You know, we're seeing all of the picture. You know, back when there wasn't color TV, there were certain things that you couldn't accentuate, you know, in the process of broadcasting television, right, which you can totally do now. In the power triangle, we have a lot more ability to understand what's happening in a circuit, because we can see how the power is distributed through each component as well as from the source. Okay? The nice thing about it is it's always the same. Now, the numbers aren't always the same, but the way you do it is always the same. Okay? Now, remember this. Okay? We're setting the bicycle motorcycle up, right? Okay? This guy In other words, the vector that's horizontal is going to represent which component in our circuit? Resistance. Resistance. This vector, which is at 90 degrees, is going to represent inductive reactance. What if it were pointing down? Capacitive reactance. And then the hypotenuse of our triangle is going to represent what? It's going to represent, it could represent Z in an impedance diagram, absolutely. But in a power triangle, it's going to represent the power coming from the source. In an impedance diagram, it would represent the impedance seen by the source. So you're absolutely right. It just depends on which triangle you're looking at. And in this case, we're looking at the power triangle. So our vector that is at 0 degrees, meaning that it is a horizontal vector, right, is going to be the vector that is dissipating watts. Okay? And the watts are dissipated in the resistance of the circuit. For sake of simplicity, we're going to assume that this inductor right here is purely inductive. We're going to assume that it doesn't have any resistance, that we've lumped the actual resistance of this inductor into this resistor here. Okay? Then back to the power triangle, the vector that points straight up or is at 90 degrees with respect to the vector that represents the real power or the watts. This is also called real or in some cases true. Power. Now, why all these names? Well, I'm just telling you that depending on what book, what article, what instructor, what application you're doing or using, they're called by different nicknames. And those are the nicknames that I've heard. Okay? I've heard real power called watts. I've heard real power called real power. I've heard real power called true power. And I've heard them all used interchangeably. Okay? So if somebody says, hey, what's the true power that's being dissipated in that circuit? You say, hold on. Let me draw a power triangle and I'll show you. And then you can show them, everything. And the true power will be the power dissipated in the resistor. Over here, this guy is VARS, and that is the power that's dissipated in the inductive reactance. That is a power that does not have any affiliation with heat. Okay? So if you could get an inductor that didn't have any resistance in it, it wouldn't get warm at all. But it would still take energy to make it work. Okay? And then the hypotenuse of the triangle is going to be the volt amperes, which is also called the apparent power. This guy is called reactive power. Okay, so that's as complicated as it gets. It doesn't get any more complicated than that. The only change that there can be to that is if you have a capacitor in the circuit. And if you have a capacitor in the circuit, then basically you have a triangle that looks like this. That's the only difference. Okay? If you have both capacitance and inductance in the circuit, or capacitive reactance and inductance in the and if you have X of C, capacitive inductance, and X of L, inductive reactance, then if these two guys are equal in length, then the total reactance or the total reactive power that your circuit will consume would be what? Would be 0. Because these guys are 180 degrees out of phase with each other. So this guy takes away from this guy. Okay? If this guy was, let's say, this long, and this guy was half that long, then what would happen is this would go away, and this would be reduced by half. And then you can see that that changes the hypotenuse of the triangle, which also changes the phase angle of the triangle. With that exception, in other words, with the exception that there could be capacitance in the circuit, that's it as far as power goes. It doesn't get any more complicated than that. You have 3 different kinds of power. You have real power, which is measured in watts. You have reactive power, which is measured in VARs, or volt amperes reactive. And then you have apparent power, which is measured in volt amperes. Now, if you go out and you buy or you look at the name tag on any large transformer, it will always be rated in apparent power. It will never be rated in watts or reactive power. And the reason is because the manufacturer of the transformer doesn't know how you're going to use the power. Are you going to use it all for watts? Are you going to use a lot of it for reactive power? In other words, what is this angle going to be? The phase angle of the circuit. The manufacturer of the transformer has no way of knowing, right? Because they're just selling you something and you're going to go use it. So they give you a volt ampere rating, and then it's up to you to figure out whether or not you're meeting the specifications of that transformer, or you're exceeding the specifications of that transformer. Okay, now let's move over, and we'll come back to our power triangle for a minute, but let's move over to our impedance diagram. Okay, so our impedance diagram in this case has 3 parts. Anybody guess what the first part of the impedance diagram is? Resistance. And that's going to be represented as a vector that points which way? That's our reference vector. And we call that 0 degrees. Okay. Then we also have, as part of the total impedance diagram, the reactance. The reactance is a vector that points which direction? Straight up and down, 90 degrees. And then we've got the impedance of the whole circuit. In other words, the impedance of the inductor and the resistor as seen by the source. Okay? And that guy is going to be the hypotenuse of our triangle. Okay? So our impedance diagram is simply going to consist of a resistance, and in this case, it's 273 ohms. It's going to consist of an inductive reactance, and that's 420 ohms. So X of L is equal to 420 ohms. So you can see I've drawn this a little bit out of proportion. This should actually be a much longer line. It's just that I'd be up here into my my wording. Okay. And then my hypotenuse is going to be the total impedance of the circuit in ohms. Okay? Now, if somebody gives us a triangle and they tell us this is a 90-degree triangle, which we know this is 90 degrees, okay? And again, why do we know that it's 90 degrees?
X of L and R 90.
Well, we can go back to Eli the Iceman as a tool to help us remember it. There's a lot of ways to remember it, but that's a tool that I like to use, Eli the Iceman. And anytime that we have an inductor in a circuit, the voltage is going to be leading the current by 90 degrees. Okay? All right. So we know we have a 90-degree triangle, and we know by the Pythagorean theorem that if we know the length of this component and the length of this component, we can find the length of the hypotenuse, can't we? Once we find the length of the hypotenuse, then we know the total ohms of the circuit, or the total AC opposition to current flow. So what's the Pythagorean theorem? Or Z equals R squared plus X of L squared, right? It doesn't get any harder than that. Now, because of the fact that you can write that down on a reference sheet, and you can have access to that reference sheet on the job site, or, I mean, there are some aptitude exams where they won't let you have any reference sheets, but most of the time, you know, in your working life, you're going to be able to have reference to that access sheet, or access to that reference sheet, rather. Okay? And so even if you forget it, you can just look at it and then boom, oh yeah, that's right. It's a right triangle. Pythagorean theorem. So if we plug the numbers in here, then we get that the total opposition to current flow of the circuit is 273 squared plus 420 squared. And so what do you get when you do that? How much? 500.9 ohms. So that's the impedance. 500.9 ohms. So as we're over here looking out from the source toward the rest of the circuit, that's what the source sees. The source sees an opposition of current flow equal to about 500 ohms, or 501 ohms. Okay? Now, if we wanted to, we could draw an equivalent circuit. And our equivalent circuit would have the same voltage. Said that was what, 50 volts? And it would be hooked up to a single load. And that single load is called impedance. This circuit here and this circuit over here are equivalent to each other. Okay? They don't look the same, but they are electrically the same. And the reason is because this amount of impedance right here is the same amount of impedance that this source sees when it's pumping current out to the rest of the circuit. This source sees 500.9 ohms when it looks out. This source right here sees 500.9 ohms. So in that sense, they're equivalent circuits. By breaking the circuit down like this, we can easily use Kirchhoff's voltage law to figure out what the voltage drop is across this impedance. What would it be? The sum of the voltages around any closed circuit equals 0. Or, when you only have two things in the circuit, then if this is 50 volts, how many volts is here? 50. That never changes. And that's the reason that we squeeze this down to an equivalent circuit, so we can do that. So if we want to figure out the current that's flowing in the circuit, we just go to Ohm's law. Current is equal to voltage over resistance. That comes from the DC Ohm's law wheel. Okay? But we know that resistance for a DC circuit is analogous to impedance for an AC circuit. Okay? They're not totally equal to each other because resistance implies that you don't have any reactive components if you only have a, R total for the circuit. If you have a Z total for the circuit, that implies that you have resistive and reactive components. So you have resistors, capacitors, inductors. You don't have to have all of them, but you've got at least two of them. Okay, so when we plug this in here, we get 50 volts divided by 500.9 ohms. And what do we get? 99.8 milliamps. Okay, so if we wanted to put that in the form of amps, then we'd move the decimal over 3 places, right? 1, 2, 3. So that would be the same thing as 0.0998 amps. Either way. We like to keep things in base units if we're going to multiply them by other things so that they don't come out wrong. Okay, now, if the current that's flowing in this equivalent circuit over here is 99.8 milliamps, or 0.0998 amps, then what would the current be flowing over here in our original circuit? Same thing. Same exact current. So the current here is equal to 99.8 milliamps. Well, if the current there is 99.8 milliamps, what's the current in the resistor? Same. What's the current in the inductor? What's the current through the source? See, so we know a lot about this circuit already. Now let's come back to the power triangle. Okay? Let's say that we wanted to calculate the real or the true power. I'm going to erase this so I can do the calculation here. Okay? If we wanted to know what the real power was, okay, then all we would have to do is figure out how much heat this resistor is dissipating, okay, in watts. So we could use any one of the 3 formulas from Ohm's law. We could use the formula that says power equals voltage times current. We could use the formula power equals current squared times resistance, or power equals voltage squared divided by resistance. We could use any one of them. So if we want to figure out the watts that are being dissipated in the power triangle, in other words, all of the power that's being dissipated in the circuit, then we'd probably want to go ahead and stay with amps, okay? And what else would we have to know? Your resistance, and that's given to you, right? Okay? So this right here, the power that's dissipated in the resistor is equal to the current squared times the resistance. So that's equal to 0.0998 quantity squared multiplied by 273. What do you get for that? 2.7? 2.7 watts. That's our true power or our real power that's absorbed in the circuit. Okay? Now, what about our reactive power in the circuit? I'm going to erase reactive power so I can write there. What is the reactive power in the circuit? Well, we can just use really the same equation. But instead of resistance, what's our opposition to current flow over here? I'm pointing right at it. 420 ohms, right. It's X of L. So the VARs, the number of VARs, are going to be equal to the current squared multiplied times X of L. Okay? Oops. So that's going to be 0.0998 multiplied by 420. So what do you get for that? 4.25. What's that? 4.2. 4.2. So that's 4.2. Would that be watts? Be VARs. Be 4.2 VARs. VARs equals VARs. Because that's reactive power. 4.2 VARs and 2.7 watts. Okay? But then along comes the person who's going to buy the transformer that's going to run this load, and they say, but what transformer should I buy? Well, the way that you figure out what transformer they should buy is by calculating the length of the hypotenuse. Okay? So the apparent power, we'll call that AP, is going to be equal to the square root of the sum of the squares, right? The square root of the watt squared, which is 2.7 watts squared, plus 4.2 VARs squared. What is that? That's equal to, is that what you get? 11.34?
Yeah, I got 4.9. 5 voltage.
Just go 7.2 squared plus 4.2 squared and then square root. 5. So that's approximately equal to 5 volt amperes. So if somebody comes along and they say to you, hey, I've got this circuit and it's really giving me some problems because I got to feed the circuit with a transformer. That's what my source is going to be. It's going to be a transformer. And my problem is that I know how much power I'm dissipating in my resistance, and I know how much energy I'm storing in my inductor. I know those two things. But what I don't know is how big of a transformer I should buy. So they come to you and they say, I got a resistor and I've measured its value. I've got an inductor, and at this frequency I've measured its inductive reactance, okay, X of L, okay, and I've gone ahead and I've drawn my power triangle. So I know that I have 2.7 watts being dissipated here, and I know I have 4.2 VARs being dissipated here. What does this guy need to be rated at? And then you can tell him 5 volt amperes. And then if people say, but aren't volt amperes the same thing as watts? Well, volt amperes are the same thing as watts if there's no reactive power. Can you see that? In other words, follow my phase angle. If I take part of these volt amperes and I get rid of them, or VARs rather, I'm sorry. If I take part of the VARs and get rid of them, can you see how my angle would change? Right? It gets smaller, doesn't it? Okay. If I were to somehow get rid of all of my reactive power, or all of my VARs, then my hypotenuse would collapse right onto my true power. So when is it that volt amperes is the same thing as watts? When there's no inductive reactance or capacitive reactance. Or in this case, when the coil's gone. If the coil's gone, then they're the same. If there's a coil, they're different. Okay? Now, most people don't know much beyond this, which comes out of Ohm's law wheel. And they've got to look at it because they just don't use it all the time. Okay? Even fewer people know that there's really 3 different types or classifications of power. And once again, there is real or true power, there is reactive power, and there is apparent power. And those are the 3 different classifications of power because of where they exist in the circuit. This is where the real power exists. This is where the reactive power exists. And this is where the apparent power exists. Okay? Questions? All right. So how many of you guys have read anything about power in your book yet? And seen the power triangle? Does it seem to be pretty consistent with the way that I'm explaining it, or are they explaining it a totally different way?
No, it's consistent.
Pretty consistent?
I like it on the board better because I can see it all on one page.
Yeah.
It makes a lot more sense to look at that when we flip back and forth.
I assume so.
Yeah.
When's the midterm?
Midterm. The midterm, the midterm, you need to turn in today. Today was